Again, the way that you can always rationalize this is that the things that require the most space, we try to get as far away from each other as possible. No, there isn't. In an octahedron, everything is exactly the same. Because the angles between all of the adjacent things are all 90 degrees. So there is no differentiation between axial and orbital. So in this case, what you do is just put them as far away from each other as possible, which is the opposite. So what we said is square. If you have similar objects like this, if you had, say, six total groups of electrons, you had, say, 3 lone pairs of electrons, what this would give you that is a T-shaped molecule as well. Then this is, if you have 4 lone pairs of electrons, this thing would again give you something that's linear. Basically, what's going to happen is that those lone pairs are going to try to get as far away from each other as possible. So anyway, all of this is summarized. And one of the things you guys are certainly going to have to be able to do, basically for any formula where you've got at least one atom that's not terminal, you should be able to use DSCPR in order to come up with both the electronic geometry, so that's the scaffolding that you use in order to describe the overall arrangement of all the electrons, as well as the molecular geometry, which is the specific shape that we associate with the atoms themselves, not taking into account the electrons. And so this table in the next couple of slides basically summarizes all the possibilities that you guys are going to have to be certainly familiar with. So if we have, say for example, only 2 groups, we can't have a lone pair, we can't have, say, a lone pair of electrons in that particular group, or else the atom will actually be terminal. And so we've only got one situation where we've got 2 atoms. So these things always give us linear, both the electronic geometry and the molecular geometry, both linear. When you have 3 groups of electrons, if they're all atoms, what we have then are what we call trig planar electron geometry, and that will also be the molecular geometry. But we can also have situations, as illustrated here, so something like SO2. I wouldn't draw the Lewis structure of SO2 like that, however. We have SO2. Take a look at SO2 and draw the Lewis structure of that. Oxygen, minus. Sulfur dioxide overall is actually a neutral molecule. And so this only has 1, 2. We should have 4. So we need +2 formal charge on this. So that means that we need to have 1 lone pair of electrons on that second atom. Because sulfur is in the 3rd row of the periodic table, we can actually make 2 double bonds. We can see the octet. So a more reasonable Lewis structure for SO2 is actually like this: 2 double bonds rather than the one that they have from here. It doesn't have formal charges associated with it either. So anyway, with SO2, one of the things that I did want to re-emphasize was that it doesn't matter if we've got a single bond here, a double bond, or a triple bond. Any bond between 2 atoms, it just gets considered one group of electrons. They might have slightly different sizes, as I described before, but it is just one group. So this has 1 group here, 1 group here, 1 group here. So it's got 3 objects around it, or 3 groups of electrons that you have to use to make the scaffolding. And so that would give us trivial planar scaffolding. One of these is the lone pair of electrons, and so the other one here are where the oxygens would be. So the overall arrangement that we see then is just like this, and so that's just the bend. So we call that particular shape bend. And so we just went over the various types of structures that we see for tetrahedral arrangements. So if you've got all four of the objects are atoms, both the electronic and molecular geometry are tetrahedral. If you've got 1 lone pair, it gives us a trivial pyramid. If you've got 2 lone pairs, it gives us another way of giving us the same sort of bend arrangement. So all we see is that we've got 3 atoms, and they're not actually all lined up in a linear fashion. So then when you go to 5 objects, these are the ones that we just went through as well. Everything's based on a trivial pyramid. And so if everything's an atom, the molecular geometry is also trivial pyramidal. You've got 1 lone pair of electrons, it's called seesaw. 2 lone pairs of electrons, give us a T-shape. 3 lone pairs of electrons, give us a linear type of matrix. So these are ones that give us as well. And then we have 6 groups of electrons, so everything's going to be based on octahedron. We have 1 lone pair of electrons that gives us the square wave sphere, 2 lone pairs of electrons that gives us a square linear. So anyway, these are the types of arrangements that you guys are certainly expected to be familiar with, to be able to identify, and also to be able to draw. And so when it comes to drawing these things, and a little bit more generally, one of the things that I wanted to point out is that we have a very simple sort of nomenclature system that allows us to describe all of these things, all of these possibilities in a very, very general way. And it's called the axe system. So the way that we describe these things, just in the most general way in terms of geometries, is by using a sort of axe nomenclature. So A is the central atom. X is the number of atoms. So these are atoms around the central atom. And E is the number of lone pairs. And so this would actually be AXN. So you can have, say, different types of geometries where you've got different numbers of x's and different numbers of d's, and these basically summarize all of the types of geometries that we looked at. And so, if we want to use this, the first thing that you can understand is that, say for example, for a linear system, or for a system where we've only got two groups of electrons around there, so for something like the one that's illustrated there, we call that an AX2 molecule. So there is a central atom, there are 2 atoms bonded to it, it doesn't matter how they're bonded to it, so the thing that they've got up there is that we have to say beryllium dihydride, or we had, say, carbon dioxide. It doesn't matter if these things are single bonds or double bonds. It doesn't even matter if they're the same atom. You could have this guy, say, something like that. It doesn't matter if they're the same. All of these situations are all AX2. You've got 2 atoms, no lone pairs, so this would be called AX2. These things are linear, so everything that's AX2 is linear. If we have, then we're looking at, say, AX3, so we've got 3 groups of atoms around there. The possibilities that we can have then are either all 3 of these things are atoms, or we can have 2 atoms and 1 lone pair of electrons. So this is how we use this particular set of nomenclature. For AX3 and AX2B, the thing is that we can draw these things very simply as well, as illustrated up here. All of those objects are in the exact same plane, so we can draw these things in 2 dimensions on say, like a blackboard very simply. But once we get to more than 4 objects, so one of the things I should point out then is that the overall number of objects around the central atom then is just the sum of all of the x's and all of the e's that are there. So this has 3 objects, 3 electron groups, and so does this. Two of them are bonds, one of them is a lone pair, but you still have a total of 3 objects around there. So if you just add up it's 2 and plus 1, you see that it's got 3 objects around it. And so regardless of whether it's an X or it's an E, you can draw these things in the plane of the board. But then once you get to a situation where we actually have then, say, at least 4 objects or more, then we have to use 3 dimensions because the things are, these objects are 3 dimensional. So if you're going to draw these things, then what you have to do is be able to use that sort of line and wedge, drawing method. So it's perspective drawing that I showed you guys before. So if we're going to draw something that's say AX4, something like methane, for example, for drawing that, the way that you draw that is you have 2 things that are in the plane. You can draw these things at roughly 109 degrees away. It doesn't have to be perfect, obviously. And then you draw that one of the next objects is coming out of the screen, and the last object is going into the plane. So anyway, this is basically, in terms of perspective drawing, this is something we want to be able to do. Because, like I said, in reality, these things are 3-dimensional objects. They're not just in the plane. So a drawing like this, which is didn't, in that it suggests that you've got a 90-degree angle between the adjacent hydrogen atoms, where in reality, as you know, it's actually more like 190 degrees. So anyway, you have to be able to draw three-dimensional objects like that as well. And so if you're drawing this instead for something like ammonia, so that would be AX3E type of molecule. Place one of these. You're just drawing the arrangement. It's not necessarily a Lewis structure, but what you have to do is you have to indicate that these things are not all in the same plane. It doesn't look like this. It actually has that arrangement, or sorry, correct pyramidal arrangement. The way that you can illustrate the pyramidal arrangement is using this perspective technique. And so, as I've shown here, again, the reason why you want to be able to do this is so that you can illustrate what the actual geometry looks like. So we've seen things like these seesaws, octahedral, square planar, and so on. And so you can use these types of perspective drawings in order to build and illustrate what the geometry is actually about. And so it's a straightforward thing to do. And we will expect you to be able to do this. So anyway, just to sort of summarize some of the kinds of questions that you might be asked to do and how you go about doing it, here is one of these: predict the geometry and angles of PCL3. So when you're doing this, whenever you've got a question like this, the procedure that you go through is pretty much always the same. The first thing you always have to do is figure out what the Lewis structure is for that particular molecule. Because you need to know how many electrons are around the central atom, and how many groups of electrons are in the central atom. So we've got PCl3. What group is phosphorus in? 15, 35. It's got five valence electrons around it. So you should, the thing is that you have to basically know where the elements are, because you have to know how many valence electrons associated with them. So phosphorus is directly below nitrogen in the periodic table. So this has 5 electrons associated with it. Each chlorine is in 17s, and then 7 electrons. So you have 21, 26. You have 26 total valence electrons. So again, if you wanted to do this, that's the sort of electron counting way. Here we've got 8 here, we've got 8 here, we've got 8 here, so it's 24. We need 2 more. So you've got a little pair of electrons on phosphorus as well. So these are all the electrons that you have for your system. You've now got your Lewis structure. And so the first thing you have to do then, once you've got the Lewis structure, is identify how many groups of electrons there are. 1, 2, 3, 4. So this we call this AX3E, which we just took a look at. We've got 3 bonds, 1 pair of electrons. So anyway, we've got 4 electron groups. Because we've got 4 electron groups, the electronic geometry is going to be based on tetrahedron. So the scaffolding that we build then is like this, exactly like what I just showed you guys. So we've got 3 chlorines, and one of the other positions is going to be occupied by the lone pair. And so anyway, then so the electronic geometry is tetrahedral. The molecular geometry is pyramidal. And so that's easy enough to do. In terms of the angles then, this is then just a question of understanding. It says what the angles would be. If it was a perfect tetrahedron, obviously these would be about 109.5. But because you've got a lone pair of electrons here, it's probably going to be a little bit less than that. So the actual angles that we can see here are probably going to be a little bit less than 109.5 because, like I said, the lone pair of electrons occupies some space. And so that's really the procedure that you have to go through. You have to identify what the Lewis structure is, figure out how many objects are around there, so the number of electron groups associated with that. So in this case, it's 4. Determine the number of bonding, number of lone pairs, as we did, and that's what you use that sort of AXE kind of implementation you want to specify that. determine what the electron geometry is and the molecular geometry. So the electron geometry, we have 4 objects, so it's tetrahedral, and the molecular geometry is going to be trigonal. And these guys are, like I said, because the first of lone pair, the angle between those is going to be a bit less than 1.945, just because the size of the lone pair is larger than the size of the other ones. So anyway, it's very, very straightforward. Why don't you guys provide this for a second or so? I'll work at this in a minute. But how about come up with the geometry angles for ICL4 minus? This is anion, I in the middle, or fluorines. ICL4 minus. So the first thing you need to do, obviously, is come up with the structure for this. Iodine is less electronegative than chlorine. They're both in group 17. Iodine is lower down. So it's going to be the central atom. So we've got 4 chlorines here. Give the terminal 4 electronegative atoms all the electrons that you need. And then you have to figure out, are there any more electrons left over? And so, like I said, you do this by counting up the electrons. So this is, each one of these has 7. Iodine also has 7. So 7. So then you've got the negative charge. That's 1. So that's 36 electrons total that you should, that you have to basically have in your structure. At the moment, we don't have that. We've got here we've got 8 around here, 8 around here, 8 around here, 8 around there. So we've got 32. We need to have 4 more electrons, so there would have to be 2 lone pairs of electrons in the iodine. The way that I do this, like I said, is sort of the same. I know that this is overall that it's an anion, so it's got a 1 minus charge. So if each of these chlorines has no formal charge associated with it, I know that the formal charge associated with the iodine itself has to be -1. And so iodine, when it's neutral, has 7 electrons around it. If it's an anion, it has to have 8 electrons around it. At the moment, it's 1, 2, 3, 4. So then, again, you put in those 4 extra electrons and the formal negative charge. Like I said, just a different way of counting up the electrons, and it's a way of checking if you actually make sure the structure is correct. So anyway, we've got our negative charge, we've got all the electrons that we need. So now we just have to take a look at how many groups there are. We've got 1, 2, 3, 4, 5, 6. So this is A, X4, B2, 6 groups. So therefore it's based on octahedron. That's your electron geometry. Electron geometry is based on an octahedron, and so scaffolding structure, we draw this like an octahedron. And so what we have then is we've got iodine in the middle, we've got chlorines, and we've got 2 lone pairs based on an octahedron. As we talked about before, the way that they get as far away from each other as possible is just by going on opposite sides. So I can say 1 lone pair here, 1 lone pair here. And then what's left over then is a square-based, square planar. The square planar structure. So this would be your actual molecular geometry. Is square planar. And so in terms of the angles that are associated with that, the lone pairs are on opposite sides. So we know here that the angle between these guys should stay pretty much exactly at 90 degrees. So in any event, that's how you go about answering any of these questions. At the Lewis structure, at the correct Lewis structure, you have to figure out the number of objects that are around that central atom, and then work from there. Use the scaffolding based on the electron geometry, and then assign the correct shape for the geometry. So it's, like I said, very straightforward. do. But you guys are probably not going to be able to make a picture that looks as nice as this. So you can use this sort of crappier perspective drawing if you want in order to come up with a picture. But really what you want to illustrate in your picture is that all four of these supporting atoms are in the same plane. You could have also drawn it like this, if you want to. You can draw it like this. You can put the load pair, say, up here at the bottom. But as long as you've got your perspective drawing right, we can tell that this actually means that they're all the same plane. This also means that they're all the same plane. Just make sure that your drawing is as accurate as possible so that we can figure out basically that you come up with the right arrangement of those. So most of the types of systems that we're going to deal with later on, and certainly if you guys are biochemistry or biology, that are doing organic chemistry here, most of the systems that you're going to deal with are things like organic molecules where you have more than one central atom. So one of the things you certainly have to be familiar with and be able to deal with very quickly is essentially what are the geometries for any one of these particular atoms. Anything that's not terminal, you should be able to assign a geometry and shape, so molecular geometry, to these things very, very quickly and accurately. So we have this is an amino acid, so it's one of the kinds of molecules that you see certainly in biochemistry and biology a lot. So we've got this amine group here, this NH2. We've got this CO2 H carbon here, which is the organic acid functional group. So anyway, if you take a look at this molecule, you can see that this is not a terminal atom, this is not a terminal atom, this is a terminal, this is a terminal. Anything that's not terminal, you can use VSEPR to assign a shape to it. And so here we've got, like I said, if you understand this AX E-type designation, you've got an AX3E arrangement here. Like I said, it doesn't matter if the various atoms are the same type, like hydrogens or different carbon. You can just summarize it as an atom by using that designation X. So this is AX3E, so we know it's based on 4 objects, and so this is going to be a trigonal pyramidal arrangement. This carbon is AX4, so that's going to be a helical arrangement. This carbon out here has one carbon, one oxygen, and one other oxygen. So that's AX3. There's no lone pair, so it's AX3 means it's going to be trigonal planar. This oxygen over here has AX2E2, so this is going to be again based on the tetrahedron, but it's actually going to be event ligation. So anyway, as illustrated in this drawing here, this is a three-dimensional depiction on the bottom. What you can see then is that the shape of this molecule really is dependent on what the actual shape is or arrangement around each one of these atoms and how they bind themselves together. And as I said earlier on in the course, so when we look at big complex molecules like this, it really does end up being the shape of three-dimensional arrangement and how the charges are distributed within that three-dimensional arrangement. It really tells us how a particular molecule is functioning, why it works the way it does. So this is one of the reasons why you have to be able to identify what the shapes are, figure out how these things can go together in order to give you an overall molecule. So as I said, in terms of why do we care about shape in the first place? What difference does it make? Well, the difference that it makes really is has to do with the properties of the molecules themselves, both the physical properties as well as their chemical properties. And so one of the things that we've been talking about before, with diatomic molecules, so diatomic molecules has 2 atoms in it, is the idea that if the 2 atoms are different, we saw that these things have a dipole. Remember, all of that means is that one end has a positive charge associated with it, one end has a negative charge associated with it. So the way that we estimate these particular dipoles, remember, is just by taking a look at what the electronegativity is of each of these atoms. So the chlorine is around 3 and a bit, hydrogen is around 2.1. So we see that this is more electronegative, so the electrons tend to be gathered around the chlorine. So we have a partial negative charge at one end, partial positive charge at the other. Remember, so one of the ways that we illustrate the presence of these dipoles is by using these little arrows, these sort of dipole arrows, where the plus sign is at the positively charged end, and the arrowhead is at the negatively charged end. But it ends up that when we're looking at most of the molecules that we look at have more than 2 atoms in them. And so it ends up how these actual atoms are arranged with respect to each other really has a major effect on whether or saw, if you look at this in the last chapter anyway, if you look at something like carbon monoxide, draw it like this. You want a proper Lewis structure. It's actually sort of a weird one. The formal charges, even though you might think that this isn't conforms to Lewis's rules, this actually is the proper structure, the proper Lewis structure for carbon monoxide. In terms of the way that the actual charges are distributed, on the oxygen side, oxygen is more like or negative than carbon. So this would be the negative end. You're looking at it. Looking at it from that sort of perspective, whereas carbon, in terms of electronegativity, we figured that this would be the positive end. Just in terms of basically oxygen being more electronegative than carbon. Because you only got two atoms in this, then you can draw that this thing has a dipole moment. Here's the positive end, here's the negative end. You can draw a dipole moment associated. But what about carbon dioxide? So if we have, again, carbon dioxide as illustrated there, for each one of these carbon-oxygen bonds, we can draw exactly that same kind of dipole. So for this one here, we've got a dipole going in this direction. For the carbon-oxygen bond in the other direction, we've got the exact same dipole, except it's oriented exactly 180 degrees away in the opposite direction. And so what ends up happening then is that you want to understand for the entire molecule whether or not it's polar. What you have to do is look at how do all of these individual dipoles interact with each other. And so this one is the same size, so the same magnitude as the other one, just pointing is oriented in the opposite direction, so they cancel each other out. So overall, when you add these two things together, which is exactly what you're expecting to do, what we see is that for the molecule itself, it doesn't have a dipole moment overall. So this, the distribution of the electrons, it doesn't have, say, a positive end and a negative end. It ends up that the distribution of electrons cancels itself out when you look at these two bonds. And so this is a contrast then, so we just looked at say, SO2. So this is CO2, this is SO2. And SO2, you can come up with exactly the same kinds of pictures, except what you see is that, okay, so here we've got this dipole like that, here we've got a dipole like that. Again, the dipoles, each of the magnitudes of those dipoles will be the same, but they're not oriented exactly opposite one another. One is pointing this direction, one is pointing this direction, but they're not opposite one another. So overall, what ends up happening then, you add these things together, is that you'll end up getting a dipole where the positive end is up here by sulfur, and the negative end is down in between the two oxygens. And so this molecule, even though it has a very similar looking formula, SO2 ends up being polar, whereas CO2 ends up being non-polar. And so, like I said, in terms of the chemistry and the properties of materials that we're looking at, these molecules, this ends up making a really, really big difference. So something like water ends up having a dipole moment. So if you didn't understand that water has a kind of shape, if you thought that water was linear, for the reasons that we just talked about here, you wouldn't expect it to actually have a dipole moment. But hydrogen is less electronegative than oxygen, so oxygen draws those electrons towards itself. So you've got a partial negative charge up here by the oxygens, you've got a partial positive charge down by the hydrogens. Because these dipole moments associated with each one of the bonds, they're not oriented exactly opposite one another. They don't cancel each other out. You have to add these things together. What we see is that overall, when you add them together, you get a positively charged region down by the hydrogens, and the negatively charged region by the oxygen. So this actually then describes how the charge is distributed in this particular molecule. And so that is then, in a nutshell, what we have to do in order to figure out whether or not all molecules are polar or not. So I'm not going to go through this in too much great detail, but I wanted to point out that we've already seen, let's say, for a situation where you've got exactly the same dipoles oriented 180 degrees away from one another, what we see is they will cancel each other out. If we have then one, we see they don't cancel each other out. You guys should be, or hopefully, are familiar with how you add vectors, at least in the simplest kind of way. So we're not doing anything numerical here. But I just wanted to remind people that when I say that the two vectors cancel each other out, we're looking at the two dipole moments, which are essentially the same thing. We've got a vector in this direction here, we've got another vector in this direction here. The way that we add them together, essentially, is we So this is our starting point, and this is 0. One vector move this over here. The way that we add these together is take the second one, move it over here, so its end point, so its starting point is where the first one ended. We can go back in the opposite direction, so when you add the vectors together, they just basically combine. If you end up back here at 0, then there's no dipole moment. If you don't end up back there, then overall there's going to be some sort of dipole moment. So when things are bent like this, so we've got these two dipoles bent like this. We take one of them here, let's take this guy and add it to that. Let's move it over here like this. What we see is that the net dipole that you get from that when you add these two things together ends up taking us down here. So it's not back at 0. It ends up giving us something that's non-zero, so you end up having a dipole. It's a very, very simple thing to do in terms of these arrows. That's all that you really have to do if you want to try to add them together. One that I wanted to show you, just because it ends up being important, so something that's trigonal planar. So the third one that we have here. Trigonal planar, it says that it's non-polar. But I just wanted to remind people as to why that is. So we've got one vector here, one vector here, one vector here. Well, let's take this particular vector. Let's take this particular vector here. Let's add this one to that one. And we go that. So that will give us a resultant vector that's down here. And this one is then oriented. It's the same magnitude. It's exactly in the opposite direction. So that's why this and this cancel out, and you end up going back to this. In any event, so trigonal planar arrangement ends up being non-polar. You do the exact same thing with the tetrahedral one, except that you have to deal with 3 dimensions. Anyway, if you're unfamiliar with, or you want to refresh your ideas about, say, hypothetical vectors, it's not really, we're not doing anything numerical, like I said. What you're really looking at to try to see is, will these things cancel each other out or not, and have just at least a simple enough idea as to whether or not they should. But most of it's summarized on this particular page. You can also look at, say, high school math books if you want to use them. Or bachelor in any event, the reason why we're interested in these dipole moments in the first place, like I said, is because it really does have an effect on how the actual molecules behave, what the properties of the overall, the resultant material actually are. And so when you have dipoles, just like with a magnet, what we see is that the opposite charges attract. And so if we've got 2 water molecules, what we see is that the water molecules actually interact with themselves very strongly. And it really does determine why water ends up having very, very different properties than a whole lot of other solvents and liquids that we're familiar with. The fact that it is polar and it has the ability to interact with itself in a very, very strong way, and ends up really, like I said, altering the properties of water considerably, as to how it dissolves things and also specific properties as well. Vapor pressure, boiling point, swelling point, so on. So if we take a look at water, the way that these things interact is we know that the oxygen end has a negative charge associated with it. Hydrogen ends have positive charges associated with them. They're not full charges, it's partial charges. But anyway, the positive charge here and the negative charge on another adjacent water molecules will interact with one another. These give rise, in terms of these types of systems, we call this hydrogen bonding. But in any event, like this is all, you're always going to see this if you've got positive charges and negative charges. There will be some sort of interaction. So this is something that we see in polar molecules. And so polar molecules can have these sorts of charge arrangements. It's also one of the reasons, as we saw earlier on in the course, as to why water is so good at dissolving, say, for example, salts, many different types of salts. Because the positive end can interact with the negative, so the anions that are in the salt, whereas the negative end can interact with the cations that are in the salt. So this is one of the reasons why water dissolves so many materials as it actually does. In contrast, if you look at something like oils, so most of the oils that we think of are just sort of long hydrocarbons. So we have something like this. So this would be hexane.